Hello, I'm MSiegel, and welcome to 7 Minutes of Circuits. Today we will discuss the power management system of a cell phone and how it relates to ECE 311, 331, and 341. We will start by breaking the power supply down into its two main components, the full wave bridge rectifier seen here, and the RC circuit seen next to it. Let's begin with the rectifier. The rectifier is made up of 4 diodes. Each diode allows current to pass in only one direction, so when the input is a sine wave, 2 diodes are on when the input is positive, and then they switch off and 2 other diodes turn on when the input is negative. Diodes work this way because of the material that they are made from. Each side is doped, one with extra electrons and the other with extra holes or positive charges. The boundary between them is called the p-n junction, and that is where some interesting things happen. Since one side of the material has positive charges associated to it and the other side has negative charges, they begin to diffuse through the material trying to reach equilibrium. As they do so, they form another electric field that opposes this diffusion field and eventually find a point of equilibrium. At this point, the charges no longer move and the region formed is called the depletion region. In reverse bias, the voltage across the diode works with the built-in electric field and increases the width of the depletion region. This depletion region is non-conductive normally, and as it increases, it becomes more non-conductive, meaning it opposes the flow of electricity more and more as the field increases. In forward bias, the voltage is applied and opposes this built-in electric field, which decreases the size of the depletion region and increases conductivity of the diode. The energy required to work against this built-in potential field is the reason why diodes have a voltage drop of around 0.7 volts when they are on. Now that we know how a diode works, we can see what will happen to an input signal when it goes through the full wave bridge rectifier. Given a sine wave input with a peak of V0, we can see that the full wave bridge rectifier would have an output shown here. The peak of the output voltage is going to be less than the peak of the input voltage. This is because of the voltage drop across the 2 diodes that it will be running through. At any given point, the current will be flowing through at least 2 diodes. When the current switches phases, it will turn off those 2 diodes and flow through the other 2 diodes. Using the graph of the signal input versus the signal output, we can find out if the circuit is linear or time invariant. If we take this signal and flip it around, multiply it by -1, we can see that the output remains the same, meaning it fails homogeneity. If we add these 2 signals together now, we can see that the input signal should be 0, but the output signal is not 0, meaning it also fails additivity. Since it fails these 2 components, we can tell that the circuit is nonlinear. Also, since the circuit contains diodes, which are nonlinear components, this circuit is still nonlinear. Now, if I turn the circuit on today or I turn the circuit on tomorrow, I will receive the same output. So from this we can conclude that the rectifier is also time invariant. Now let's move our attention to the RC circuit shown here. If we give the RC circuit an input of a unit step function, we will find out the output is shown here. This is showing that the capacitor is charging based off of the value of tau, which is the value of the resistance the capacitor sees times the value of the capacitor. This output results in a unit step response of the RC circuit. If we take the derivative, we can find the circuit's impulse response, and using the impulse response, we can calculate what the output will be for any given arbitrary input. Using the impulse function, we can now send the RC circuit a square wave input and see what its response would be. Then we can flip the square wave upside down or multiply it by -1 and see what the output would be. Shown here, you can see that the output follows the input, and so the circuit is linear. Now, if I turn the circuit on today or if I turned it on tomorrow, I would get the same exact output response, meaning a time change of 24 hours would not change the output, meaning the circuit is also time invariant. Now we can combine the 2 circuits, the full wave bridge rectifier and the RC circuit. When combined here, we can see that the circuit, because of the full wave bridge rectifier is nonlinear, the entire circuit is nonlinear. but since both components are time invariant, the entire system is also time invariant. If we send that same sine wave into the rectifier, you can see its output shown here. Now when this output goes into the RC circuit, you can see that circuit output here. What the RC circuit is doing is the capacitor inside the circuit is very resistive to changes in voltage across it. It does not like instantaneous changes. So its voltage changes slowly. Since it's parallel to the output load, the output tries to stay at the same voltage when the input voltage changes. So in the graph shown here, you can see that the RC circuit is stabilizing the output and reducing the drop as the input voltage drops. This results in an almost DC-like output voltage. And that is how power supplies work in our cell phones. Thank you for watching, and join us next time at 7 Minutes of Circuits.